In this video, we're going to implement different block types and use random noise to procedurally generate terrain. So now that we have this basic chunk created, we're going to start defining some more interesting block types to use. First, we're going to make a new scene. It'll be a 3D scene, and let's call this level. And this is going to be our actual game level. So let's go ahead and save that. And we will instantiate a child scene. We'll give it a chunk to work with. Now we're going to add another child node, and we'll just make this a base node, and we're going to rename this to block manager. And what this is going to do is it's going to keep all our data about our blocks, and it's also going to generate a texture for this chunk to use based off all the blocks that we've added. So we can save this again, and we'll do attach a new script, call it block manager, and here it is. And much like all our other scripts, we're going to add the tool attribute to it because we want it to run while we're in the editor. Now let's define a few blocks that we're going to have in our game. So we'll start with an air block. I love the suggestion there to go from air to bear. No thanks. I'm going to call that stone instead. Export public bone. No, it's going to be dirt. And lastly, let's see what it suggests here. Bone again. Nope. It's going to be grass. So those are our block types. Next, we're going to make a dictionary. Make it read-only. And it will map from a texture 2D to a vector 2I. And what we're essentially going to do is we're going to make a texture atlas out of all of our block textures. And this is going to map from an image to where it is inside of that texture atlas. If you followed like the previous tutorial I did on this, you might be familiar with the whole texture atlas thing, so we use that there. I think this is a better way of doing it just because it makes it a lot easier to add new blocks by just adding a new texture. I'm going to call this atlas lookup, and we're going to instantiate it to be a new dictionary. Next, we're going to define the size of the grid that we're going to draw all of these images to and create a texture atlas out of, where the grid width will be fixed at 4, but the grid height will be variable because as we add new images, it'll just keep getting taller. We'll keep adding more rows to our texture. Next up, we're going to add a vector 2I, which will be the block texture size. If you remember before when I showed, whoops, why did it do that? When I showed the textures I made, they were 16 by 16 pixels. So if you want, more resolution in your textures, you can modify this, just make sure it actually matches their sizes. And then that should just work. Lastly, we're going to define a texture atlas size. Get private set because we only want to set it in here. And this is essentially going to give us, these values once it's done generating our atlas of textures. And I'm leaving it as a vector 2 instead of a vector 2I because I'm going to do some division using these values later on, and integer division can get weird with rounding and stuff like that, so we're just going to keep it as a float. Lastly, and this is part of the reason why I'm using C#, is I like using static classes or static instances. So this will allow us to access our one block manager from our chunk script and later on from our player script. And I think this is the last thing. We're going to define a standard material called chunk material. Sometimes the autofill is really annoying. There you go, get private set. So once we're done generating our atlas of textures, we're going to make a material, and we're going to use that material in all of our chunks. Right. Now this is going to be some of the more complicated code in this. So, I mean, if you really don't get it, you could just manually define the chunk material and create a texture atlas, but I don't know. I like this one. First, we're going to set our static instance to be our current class. Now we're going to use some LINQ or LINQ. I don't actually know how you're supposed to say it, but it's a way of doing stuff with arrays that's very useful in C#. So we say we're going to define a list of all of our block textures. And actually that reminds me, if we go to our block script, blocks do not have textures yet. So let's do really quickly export public texture 2D texture. Get set. And this should be a capital T actually by convention. And for now, the blocks will just have the same texture on all faces. We'll come back and add to this later on once we actually have it working. So we want to get all of our block textures. To do that, first get a list of all our blocks: pierre, stone, dirt, and grass. Then we're going to call select. So you can see now it's using system.linq or .linq. I have no idea how you're supposed to say it. And with this, you basically give it in a function. So this would be that it takes our block, and from that block, it gets the texture. Next, we're going to add in a where, which will check texture, where the texture isn't null, right? Because say for our air block, it's not going to have a texture. So we want to filter that out. Lastly, we call, no, it's not unique, it's distinct. So for this will be, say for example, our grass block in the future. The underside of a grass block looks identical to a dirt block. So the texture might appear here twice. So we use .distinct to make sure we only take it once. And lastly, we'll do toArray, just to get this back into a more familiar form. So there you go. If you haven't used inline array modifications, and good luck. Now we're going to loop through all of our textures. So for int I equals 0, I less than the length of our textures array. We're going to grab the texture and we're going to add it to our lookup table. Texture, and it's going to take in a position. So basically we're going to take, its index and figure out where that would be as we go along the rows left to right. And every time we get, to grid width, we go down to the next row, down to the next row. To do that, we do new vector 2i, take I modulus grid width, and then for the y, we're going to floor to int I divided by the grid width. And I'm missing some brackets. Next, we're going to determine what the grid height is. For that, we'll do ceiling to int. So basically this just means round up, and we're going to do, well, the suggestion is close to what we want to do, but not quite. We're going to do the length of our block textures and divide by the grid width. And I think actually I have to cast this to a float, else it's going to do integer division and it's going to mess up. So this would again be, if we had 5 images and the grid width is 4, 5 divided by 4 is 1.25. But of course we can't have 1.25 rows, that makes no sense. So it's going to round it up to 2. So we're going to have 2 rows, just the second row isn't going to be completely full. Now what we're going to do is we're going to create an image that's going to contain all the textures from all of our blocks. And this, excuse me, this image is going to be in pixels, right? It's going to be the number of images we have going widthwise times how wide in pixels each one of those images are. And then similarly for the height, do the grid height times the actual size of the texture. Now for this we're missing, so it takes in use mipmaps. We're just going to set that to false. I'm not even sure what mipmaps are. And for the image format, just use RGBA 8. Again, not entirely sure what the optimal value is for that, but this has worked for me, so we'll just use that. Next, we're going to loop through every texture in our grid. And this is where we're actually going to start adding these textures to our main image. So for that, from the XY coordinate, first we're going to get the image index. This is just sort of the inverse of what I did here, where for this it's going to be x plus y times grid width. Now, like I kind of mentioned here, when we rounded this up, the last row might not be entirely full of images. So we're just going to check that our image index, if it's greater than the number of images, then we'll just continue and eventually it'll finish looping. Otherwise, let's actually get the image for that block. So for that, we're going to index into our array of textures, and then we're going to call getImage. So this is a method on a texture 2D that copies the data from the texture and makes an image. Next, we're going to convert that image to make sure that it is the same format as our large image that we're creating. And lastly, we're going to draw into that large image using the blitrect method, which is going to copy in the pixels in a rectangle. It's going to copy from current image. It's going to take essentially everything in that image. So for that, we define a new rectangle that starts at 0 and has a size that's equal to the entire size of the image. And then the position that we're going to copy it into is going to be xy, but multiplied by the size of each texture, right? Because this is the specific pixel position that we're going to draw it into. So now we've drawn everything into our image, so we can actually get out of this for loop. So our image now contains all our blocks. Now what we're going to do is we're going to create a texture from that. We're going to call it texture atlas. And for that you do image texture dot create from image image, and this returns a image texture type, which we're then going to use in our chunk material. So we're going to make a new chunk material, and in here we will set its albedo texture to be texture atlas. Another very important thing that we're going to do in here is set its texture filter to be nearest. And essentially this is what you use when you're doing pixel art and stuff like that, where you want it to actually really make the pixels really crisp. I don't know what I'm saying there. But otherwise it sort of blends them together and it looks really, really bad for pixel art. Now with that all done, we're just going to set our texture atlas size to be grid width, grid height. That's going to be really important later. And just as a bit of a sanity check, we're just going to print out the size of our atlas, how many blocks we made it out of, just to make sure that this actually worked. And with that done, the only thing left is to actually make it so we can access this dictionary and actually read from it. So for that, we'll make another method called getTextureAtlasPosition. That's going to take in a texture 2D, and it'll say, given this texture, say it's the dirt texture, it'll tell us where in our material that image is actually located, so that the chunk can actually render that texture properly. The next thing we're going to do is, just because we're a bit paranoid that maybe we're going to be asking for a texture that's null, if that happens, just return 0. It'll just default to the first block in the texture, which is fine. Better than it failing horribly and throwing errors. Otherwise, we're actually going to index into our dictionary and return the position of that texture. So now that this is all implemented, we can go into our chunk script and update it to actually use the material that we've created and actually change the generate method so that we get different blocks. So let's remove this line where we were creating that placeholder block. Instead here, we will define block, and now we'll do some if statements to see which blocks we're going to use. So I think for now, I'm going to define a variable called ground height. We're just going to set that to 40 for now. In the future, we'll use some random noise to procedurally change the height of the terrain. But as a placeholder, let's set it to 40. Now, if our y value is less than, let's say the ground height divided by 2, so it'd be less than 20, then we are going to use a stone block. Else, if it's just less than the ground height, we will use a dirt block. Else, if y is equal to the ground height, so we're at the surface now, we will use a grass block. And finally, for above ground, we're going to use an air block. Then we're going to set our block to be equal to that block. Of course, this would work for now, but we're not actually doing anything to use the textures of any of those blocks. How we do that is here, before we commit what we've created in our surface tool to our mesh, we're going to do surface tool.setMaterial, and we're going to tell it to use the chunk material that we created in our block manager. Now here we're creating the block mesh. Firstly, we're going to want to figure out what block are we actually generating. So to do that, we will get the block at the block position. Now we're going to do a bit of hard coding. If you were to actually extend on this and add more blocks, you'd probably want to change how this works. But for now, we're going to say that if we're making an air block, just return. Don't create a mesh, don't do anything, just return, right? Because you can't see the air, you can't touch the air. Well, you don't collide with the air, so no point in even doing anything. Now if we look at create face mesh, we're going to want to take in a texture. So we're going to add a parameter to that, texture2d texture, so that way we can actually draw the texture that we want to make. And of course now it's complaining that we're not telling it which texture to use, so just add block.texture to all of these. And again, in the future we can come back and change this so that the top texture can be different from the bottom texture, different from the side texture. So we can change this in the future for that. We go down to create mesh face. There's a few things we're going to want to do. First, we want to get the position of that texture in our texture atlas. So we'll do blockmanager.instance.get texture atlas position, and we're going to give it our texture. Next, we're going to want to get the texture atlas size, which is like this, and I'm just doing that so I don't have to write out this entire thing every single time. Now what are we going to do with these? If you're somewhat familiar with 3D modeling, you've probably heard of UV unwrapping for texturing models. So we're going to figure out our UVs, which is the location in our texture atlas of each corner of our square that we're drawing. And that's done as a value between 0 and 1. So this position here is given in terms of pixel coordinates, right? But we don't want to use pixel coordinates. We want to use a value between 0 and 1. So to do that, we just divide our texture position by our texture atlas size. We also want to get the width of our square in terms of UV coordinates. So to do that, say the texture atlas size is like, 4. So that would mean that we have 4, blocks. Say the width is 4, so we have 4 blocks per row. So that means that if we're going from 0 to 1, each block is going to be 0.25 wide. And then similarly for the height, we do 1 divided by the size in y, in the y direction. Next, in much the same way that we've defined every corner in like physical space, we're going to define each corner, the UVs of each corner. And for that, we first start with the UV offset, because that's sort of the position of this square that we're drawing, or that we're getting the texture in. And firstly, this first corner is going to be, say, in the top left. The next corner is going to be in the bottom left. Third corner is going to be in the bottom right. I'm also seeing that I made a typo. Go back, fix that. And lastly, in the top right. And if you remember when I was talking about these ones, they were also in top left, bottom left, in the same order, because again, the order is very important here. And then in the same way that here we defined the triangles, we're also going to want to define the UVs for each triangle. Just this time they're vector 2s because they're the positions on the texture. And again, pretty much exactly the same, where it goes A, B, C, and then A, C, D. And lastly, down here, got to rename that to triangle 2. Lastly, down in here, we also pass in, you can see the next variable that I would take in would be the UVs. So we give it UV triangle 1. And down here, UV triangle 2. I think we're almost there now. One last thing to do is, now that we actually have, a block that is transparent, that being the air, we can actually make this use the block that's actually at that position instead of just returning true. So I'm going to copy paste some stuff in. So basically here, this is just making sure we're not going out of bounds, right? So if we're at the very bottom of a chunk, we are going to render those faces because there's just void essentially outside of this. So we will always consider those to be transparent. Otherwise, we check the block at that exact position, and if it is air, then it is transparent. And again, if you were to extend this and add new block types, maybe you would add, to your block class a parameter that says if it's transparent or not. So if you were adding like leaves or something like that, maybe they would be transparent. So this is left open for extension. I think with all that done, we can go back to our editor, build our project, and when we look at our block manager, we can see exposed in the editor, we have the air, stone, dirt, and grass. If we click on this, because we use the global class attribute, we can define a new block. We can do that for each one. If we open up the block, we can see it takes a texture. So for air, we'll leave the texture null. For stone, we can drag in that texture. For dirt, drag in that one. In grass, drag in that one. If we save our scene, close it, we can close this old chunk scene as well, and open the level back up. We can see it's broken. Okay, I see. I've had this problem before. I'm not sure why this happens, but yeah, if I check my import here for these images, it imported them weirdly. It thinks that they're meant to be compressed. Yeah, like this one is lossless. This one has VRAM compression. Don't want any of that, so I'm going to select all of them. Click here, Preset. Click 2D, and then click Re-import. Now if we save, close the scene, and reopen it, now it's actually working properly. So not sure why it does that, because the first time I tried any of this, it didn't do that at all, and it just worked. And then the second time I tried it, it happened. Not sure what that's about. But now there you go. We actually have different block types. So what we can do now is we'll go in here and let's modify our chunk one last time to actually implement some random terrain. For that, what we're first going to do is we're going to define a new vector2i called chunk position. And essentially what this represents is the position of this chunk in the larger, tile set of chunks. So you'd have, your chunk at 0, 0, your chunk at 0, 1. This essentially defines where every single chunk is going to be. In our ready method, we're going to want to set that value. So we'll do chunk position equals new vector2i mathf.floor to int, and this will be the global position of the chunk divided by the width of a chunk, and then again mathf.floor to int the global position.z of the chunk divided by the depth of the chunk. We're going to use that value down here, where we're going to alter our generate method, where we want to get the position of this block in the world. So that's going to be at the chunk position times the size of the chunk. And you might think this is a bit redundant, that up here we've divided by the size, and then here we're multiplying by the size. Oh, I forgot to write new. And you're right. It's just because in the future, later on in this project, we are going to modify how this works, and you're going to have to do it like this, else it breaks. So currently, yeah, it's a bit redundant, but in the future, it's going to be very important. So this is the sort of real-world position of the chunk itself, and then we're going to add on the x and z position of the block. And we're going to use that position to look up in a noise generation object, and we're going to get some random noise, and that'll be our ground height. So for that, we're going to export a public fast noise light instance. We're going to call that noise get set. And instead of just setting the ground height to 40, we will do noise.getNoise 2D at the global block position. Now this returns a value between -1 and 1. So we're going to add 1 to it, which now gives us a value between between 0 and 2. And let me check, why is it complaining? Oh, it does not take in a vector. Okay. Position.y. So yeah, getNoise2D gives a value between -1 and 1. We add 1 to get a value between 0 and 2. We then divide by 2 to get a value between 0 and 1. And then finally, well, actually, not quite finally, but we're then going to multiply that value by the height of a chunk. So that now gives us a value between 0 and 64. And lastly, we're going to cast that to an integer. So now with that, our ground height can vary randomly, and it'll use random noise to do that. If we go back to our level scene, we're going to build it. Then on our chunk, and actually we can go into the chunk scene itself for that. Be a ton of errors now when we open up the chunk because it's expecting there to be that block manager that's in the level. So that's fine. We don't need to be in this scene, right? So here we can define the noise for it. Just do new fast noise light, and we can just leave it with the default values for now, but you can tinker with these to get different terrain generation. We now go back to our level. We can see it's now using that randomly generated terrain, and we actually get some varied terrain height. Now if we add another chunk to the scene, I'm holding control while moving it to have it snap to the grid. You can see that at the start it looks identical, but if we just reload the level, since it's based on the actual position of the chunk, we're actually getting some smooth looking terrain. We can add in another chunk. Is that, yeah, that's lined up well. Add in another chunk. And again, if we save and reload, you get some smooth terrain going around. One thing you're going to want to avoid is don't duplicate the chunks, because when you do that, when it duplicates these values over here, it doesn't say, you know, in the duplicate, the collision shape doesn't point to the duplicate's collision shape. It points to the original collision shape of the object it was duplicated from. I don't know why Godot does it that way. I think Unity does it the other way, and that's why I expect it to be that way. Because I'm more used to duplicating things in Unity, I guess. But yeah, just a little pitfall to avoid. Right, there's one last part that I forgot to implement, which is if you look at the grass blocks, you can see they don't have like a nice side text or anything like that. So we're going to fix that up. Actually, let's go into the block script first. So here we're exporting just the texture. Oops. I'm going to copy that line twice. At this one, we're going to call it the top texture. Here, we're going to call it the bottom texture. I'm also going to write a helper method called textures. We're writing this as like a property get, which is why this is written as an arrow. And it's going to return a new array, which is going to have texture, top texture, and bottom texture in it. And the reason why this has to be an arrow here is because if it was just an equal sign, these values don't exist yet, right? So when we do this, it just means that when this gets called, it's going to make this array. And what this method here is for is just to collect together all the textures that this block uses for the block manager. So if we scroll down in here and we look at where we're getting our block textures, see right now we're just getting the one texture. Instead, we will get all the textures. However, this is an array of textures, meaning that now instead of this just being an array of textures, it's an array of arrays of textures. And to fix that, just change select to select many, because what this does is it applies this, and then it flattens the result down into a single long array. So instead of an array of arrays, it's just one long array. So with that implemented, it's now actually going to be, looking at all 3 possible textures that we can have here. Next, we go into our chunk, and in here, in create block mesh, as I mentioned before, we can now modify this to use the top texture. But what if you have something like stone where the top texture isn't distinct from the side textures? In that case, we'll leave the top texture as null. So what we can do is use the null coalescence argument, or operator, rather. And what this does is, if this value is not null, it just uses this value. But if this value is null, then it will default to this value over here. So it's a very useful operator. Now similarly, we do the same thing for the bottom texture, where it'll use the bottom texture if it is not null, otherwise it'll default back to the default texture. So now here, we go back in here and we rebuild. Now see that there are all these extra textures that we can define. If we go down here to our grass block, we will change the default texture. There's now like the side texture, right? So we will use our side texture. For the top, we'll use the grass, and for the bottom, we'll use the dirt. And now if we restart our level, we can now see that it's using the appropriate texture for the side, a different texture for the top, and there is a different texture for the bottom. We just can't see it right now because those are all underground. So there you go. That's we've now finished up our sides. And then if say you did want to go ahead and like define a block, say like think back to Minecraft, a furnace has different textures on the front as it does the left and the right. So you could change this to have a different texture here, stuff like that.